communicated with him properly. You know, we
Yeah, it's all right.
but that's the reason for it. But then when you come here, you see what you find is the wave equation, Bernard, which is just got the quantum potential. That makes all the difference. That makes it quantum.
Yeah, yeah.
Okay, and then the weak values, which you turn out to be these energy momentum tensors here, and you find here is the weak value
Okay.
for the field momentum.
Yes.
Okay, well, sorry, here.
Yes. Well, of course I know it. Yeah. I
Yeah,
know that.
okay.
Yeah.
And then you work out what that weak value is, and you find it's in fact the weak value is the Ponting vector. It's quite beautiful the way it looks
So
as
the
if
weak value itself is
It's
just
the pointing, yeah.
yes, but it's the weak.
The weak value of the pointing vector is
Why
slightly
do I
different.
say
yeah.
weak? Look down here. Here is the energy moment. Here's the energy.
Yeah.
There's 0, 0.
Yeah,
There's the usual energy,
yeah.
but there's some more energy there called QA. Where QA
There's a quantum potential
And
energy,
QA is...
is this thing here.
Oh, okay.
and that's a quantum effect.
Ah, okay. So it's a... Oh, I see.
And
It's a
it's that.
fluctuation. Yeah.
And it's that makes that weak.
I see.
Isn't
so
that
this
beautiful?
So it's these are like the fluctuations, quantum fluctuations. What's R?
R is the amplitude. It depends. This is why we said it depends upon the form of the wave function.
Okay.
Yeah.
Because R is the amplitude, which gives us an idea of the form, and
Yes.
that's why we then said it's the
That's the way it's
form.
written, the fluctuation.
Oh, I see. So and that's the...
And that's then you
And A is the normal vector potential.
yeah. This is
So
in the
that's
Coulomb gauge.
in the Coulomb gauge. Okay, so that's...
Yeah.
Can I interject something?
Yeah. Sure.
If you're dealing with quantum fluctuations, I've got...
Well, I wouldn't call this a fluctuation.
No, he's not. It's a quantum potential.
It's a quantum potential. It comes
Yeah.
from the
In
wave
Bohmian.
function per se.
Yeah.
This is why I haven't gone into open systems.
I'm
'cause
working on a way that you can make a quantum, what I call a quantum fluctuation, observable.
Yeah. No. Okay.
Okay, but that's.
But this is not what we're doing.
It's not. It's not a
That's
random
fine.
statistical
No.
fluctuation effect. That there could be connection, but not.
Okay.
Right.
Maybe
But-
I should consult you about
Yeah, well,
Yeah, you
well,
probably should.
You see, one of the things that one can also measure here is this weak value is a complex number.
Yes.
yeah.
So it's got an imaginary part,
Yeah.
and the imaginary part is the osmotic velocity.
Ah, now that's important.
And that's connected with what Ed Nelson did, trying to get quantum mechanics out of a statistical theory. Remember Ed Nelson's
Yeah.
quantum mechanics from Brownian motion?
Yes. Yes. And by the way, Sutherland neglects that. He takes only
Okay,
real
yeah,
values.
yeah, everybody takes real values, but
Yeah. Okay, so that's one of the reasons.
it's
Okay.
important for me because the osmotic momentum is
It's Q which is complex. Is that right? Or
No,
which
Q,
is,
that's
which is
real.
the complex thing?
that's
No, no,
real. No,
no.
this is complex.
Ah,
Yeah,
it's
yeah.
these. This is the
It's,
stress.
so the Ponting vector is complex.
Ah, I see. The pointing vector. Is
Sorry, I'm taking the real part throughout here,
Okay.
but the Ponting vector has a
The weak value of it. The
yeah,
weak value has
of it
a
has a
which has a physical interpretation as the Nelson osmotic
the
velocity.
weak value is associated with the fact that it's complex rather than real.
yes.
Yeah. Yeah.
Yeah, and then of course eigenvalues are all real, so they come out at the end of the line, as it were. So you're not denying them; you're just saying there's more information in a quantum system than you think there is,
Yes.
Oh, I'm glad to hear you saying that, because I've
and you can get at it.
I've decided that insisting on real eigenvalues is a false economy.
I agree with you on that. I agree with you on that.
And,
Okay, so that's
Good.
my
That's
main
it.
message.
Yeah.
Keep talking.
This is my main message.
Basil, can you maybe write up something a little bit about the meeting?
I'm
What-
writing up something.
you're right,
like
okay.
it. I've
And
got
you
this. I told you I've got the paper here. Which I
Okay.
was,
Did you send me this? You didn't send
No,
me
I
that
didn't.
yet.
'Cause it's
Not-
only
But so
red
What?
hot
with
off
these-
What?
just off the press.
Oh, just off the breath. Okay.
So when the experiments they're doing at UCL, are they going to be measuring this actual? Is this what they're
Yeah.
actually
Yes, yes,
measuring? This
with
actual effect?
argon atoms.
With argon atoms.
Yeah.
And
And
so they
helium.
can actually verify that it is actually this precise formula which
Yeah.
is going to...
That's what our ultimate aim is.
There are
Yeah.
weak argon atoms, did you say?
No, weak measurements on argon.
Yeah. But you're not measuring the imaginary part, only the real part.
No, we can measure the imaginary part.
So you can do both.
Both, yeah.
Oh, okay.
And it's the imaginary part which is nabla R. This one's nabla squared.
Yeah. Yeah.
Yeah, nabla R. If that nabla R doesn't exist, you don't get the quantum potential out.
Okay.
So that's the energy of
Now,
this osmotic.
does the imaginary part have anything to do with fluctuations and what he's worried about?
Well, it
Because it
comes-
doesn't matter.
it really comes from the fact that you do not have a continuous differential.
Right, okay.
So you have a differential, you can define it coming from the past at x, taking the first term of at x, a future term.
Okay, so there is your,
Yeah.
so why don't you like retrocausality? You just said it,
No,
right?
I know, it's here.
Okay, it is there.
But it's
Right.
not, it's saying that you've got an ambiguous way of defining your differential coefficient.
Yeah. But,
You're at a point here. Now, are you talking about the differential that comes from the past or going to the future?
but why not by time
Well,
reversal
you
coming
can
back
do
from?
that. You can
Okay,
do that.
that's
I
a
just don't want to
U
do that.
price.
Are you
Okay.
suggesting that the particle is a sort of a moving discontinuity?
Yeah, but it's not a little billiard ball running along a track.
Oh, so you think it's a phase discontinuity?
There's a change. There's
There's,
something.
like-
I don't know what it is.
There's
But it's
some
not a
some
particle.
structure in the phase?
Yes.
that's very
Non-conti-
fascinating.
oh, okay, well that is
Some
good.
structure of the
Very
Well,
process.
but
I'm talking
doesn't
about
that
the
get,
process.
doesn't that get back to de Broglie?
And then when you start, and the bone theory and the Dirac theory only works below pair creation. If you have energies where you allow pair
Yeah.
creation, you've got to go to field theories.
Yes, yes.
Eh? Pair creation.
Pair creation, yeah, electron positrons, you know.
Then,
Antimatter,
then you're going to the full wave theory.
yeah.
So what we're looking at is the low energy behavior.
Yes.
And that's with the particle with the Schrödinger weak value, it actually becomes, I've shown it, take an upside down harmonic oscillator with a little Gaussian packet on the top of it. There's a quantum potential in that Gaussian packet, and watch the particle go crash, there's inflation. Watch it go crashing down. The kinetic energy gets bigger and bigger and bigger, the quantum potential is negligible. And you can actually show there's a translation between the quantum trajectory and then it smoothly goes into the classical trajectory.
So you can actually do Bohmian cosmology this way.
It's like inflation. It's like
Yeah,
inflation.
that's what I got it from.
Yeah.
I see. I see.
Inflation.
Okay, yeah,
Well,
and
my idea
cosmology,
at one stage was
there's an analogy.
that the classical world emerges from a quantum, we got a quantum fluctuation which it was supposed to begin. You guys are telling us that.
Yeah.
Now, I don't know whether I believe it or not, but let's take it as a proposal.
Again, this is what I need to have a conversation.
Then if you leave it there and you let inflation take it, and I think Gustav Klein gave me this clue.
Yeah.
And then I just did this naive little calculation and I showed the trajectories you can actually map them. Quantum trajectory goes smooth.
Yeah.
Now, why can't you do that with a photon? Because you can never get the photon to go slow enough
Right.
to produce the classical trajectory. All you ever do is get a field. And
So this
that's
is
why-
only for massive particles,
Yes,
that's
it's
like
only-
the argon atom,
yeah.
yeah, okay, gotcha.
Okay.
Right.
All right, I think I might have